Faraday, as a scientist, was thinking that whenever there is a change in flux, an EMF is induced. In simple terms, when a conductor is cutting the field lines, an EMF is induced. So this is the main idea, that whatever you are doing to change the flux, it will induce an EMF. And if the direction in which flux is being changed is reversed, the direction of induced EMF also reverses. This is the first example. You have a conductor and this is a circuit. This is a circuit. You can notice one thing, that in the circuit, in this circuit, there is no power source. There is no battery. There is no cell. Why there is no battery? There is no cell? Because you are going to generate electricity yourself. So you can notice here that the wire is cutting the field lines. When you move the wire up and down, the wire will be cutting the field lines. Faraday suggested that if the wire will be moved externally, the meter will show some deflection. As the wire moves, field lines are being cut. Acha, this is a concept I always refer to. Example of, for example, if you have a chance of swapping the wireless cards, like the cards which have a chip on it, and you have an attendance machine, and you bring the card near to the machine, you can notice that machine read it. This is called detecting field lines. These are called cutting the field lines. And this is an idea of field interaction. Just like a walk-through gate, when you go through a walk-through gate, you can hear a beep sound because you are cutting the field lines. And this is an example of cutting a field. So this is the idea of some examples of EM induction. So first you have to copy this screen.
Done, sir.
If the direction in which flux is being changed is reversed, the direction of induced EMF also changes. You have to copy this screen. I'm just coming, copy this screen. This is the first example. Copy this screen. There is a wire, and again, notice a very interesting thing to remember, that when you are given a question in electromagnetic induction chapter, this circuit won't be having a power source. Why it's not having a power source? Because this circuit is going to generate electricity like a generator. A generator is never inserted in a power socket. Why? Because generator is going to produce electricity. So EM induction chapter, circuits do not have any power source. Let me know once you have copied it.
Yes, sir, I'm done.
Good. So you will move the wire. You will move the wire, and the wire will be cutting the field lines. The wire will be cutting the field lines. The wire will be cutting the field lines, and then there will be a flux change. You have to copy this screen. Copy this screen. I'm just coming.
Done, sir.
Look at the observation. Faraday observed that until the wire is moving, meter shows deflection. But when the wire is at rest, meter shows no deflection. If you move the wire faster, you will get more EMF. And he notices that mechanical energy converts into electrical energy. You have to copy this. Now, so look number 5. If the wire is cutting the field, EMF is maximum. But if you move the wire parallel to the field, you're not cutting the field, then there is no EMF induced. A very technical concept. You have to copy this.
Done, sir.
Right. Now, why there is no why there is no force, now there is no position here. When F is equal to QVB sine theta, theta will be equal to Z90. So the interference will be maximum. But when you put theta 0, obviously the force will be 0 and interference will be a minimum in the second case. When conductor moves, flux being cut, and this is the force F is equal to QVB sine theta. This is considered to be one of the most important concepts in A-level physics. What happens in this chapter? This is a memory from O-level also. Majority people refers to Faraday law. Majority people refers to Fleming's left-hand rule for the induction, right-hand rule, sorry, for the induction of current. But CI says that neither Faraday law nor the right-hand rule justify the origin of magnetism, origin of magnetic current. In my last class, I had explained that why an EMF is induced, when a conductor is cutting the field lines. When a conductor is cutting the field lines, the electrons inside the conductor experiences a force due to which they gather on one side, due to which an EMF is induced. You have to write under it, when a conductor is cutting, the magnetic field lines, when a conductor is cutting magnetic field lines, the free electrons gather on one side of the conductor. This is the origin of induced EMF. Now copy this screen.
Done, sir.
Look at example 2, one of the most famous example for past paper. This is a long solenoid. Again, notice that there is no conductor, there is no power source in the circuit. The bar magnet is moving towards the solenoid. Copy this example 2.
Done, sir.
An electric current which is flowing in a conductor generates a magnetic field around the conductor. In 1820, the experiment conducted by Ørsted showed that electricity could be a source of magnetism. But could magnetism also be a source of electricity? In 1821, Michael Faraday began researching ways to produce electricity from magnetism. However, when any conductor was placed near to a magnet, no current occurred. After years of fruitless attempts, in 1831, Faraday made a significant discovery. Current occurred in a conductor only when changes took place in the system. For example, during the movement of a magnet. The effect is much stronger when the conductor in which we want to induce the current is coiled into a solenoid. An electric current which is flowing in a conductor
If we connect a solenoid containing a large number of coils to a sensitive ammeter, then as the indicator of the ammeter is not deflected, there is no source of voltage. We will now conduct an experiment. We slowly introduce a bar magnet into the center of the solenoid. When the magnet is finally at rest in relation to the solenoid, we can observe the readings of the meter. The hand continues to indicate 0. Therefore, there is no flow of current. So, we need to question whether the assumption that a magnetic field induces a flow of current might be wrong. This time, let us try to move the magnet into the solenoid more quickly, while continually observing the indications of the ammeter. We can see that, as the magnet is being inserted, the hand of the meter is deflected. However, once the magnet is inside the solenoid, the hand again indicates 0. Let us now move the magnet quickly out of the solenoid. The hand again deflects, but this time in the opposite direction. After a while, it again reads 0. Let us sum up our observations. An electric current can be produced when a solenoid is placed in a variable magnetic field and the circuit is closed. If we connect a solenoid, let us now study the different ways of generating an induced current. We already know that it can be generated when we move a magnet into and out of a solenoid. Of course, we could equally well leave the magnet stationary and move the solenoid. Instead of a permanent magnet, we may also use a magnetic field, which has been produced by another solenoid. We can bring the solenoids close together and then move them apart. A change in the magnetic field may also be induced by changing the current which is flowing in the solenoid. We can also break the circuit by switching the current on and off. Let us now.
So there is a series of animations you saw here, and I hope if you can understand the fundamental point here, that whenever a conductor is moving in a magnetic field, you can generate an EMF. It's a concept of induction of EMF. So we made this concept. Please
In
go
the
ahead.
animation, they said variable field. What's a variable field?
You can, this is a very good question. It means you can alter the magnetic field also if you do not want to move the conductor. The main concept here is the change in flux. So either you move the magnet or you move the conductor, or you alter the magnetic field by any possible way. It means there must be a change between a conductor. There must be a change between a conductor and a magnetic field. Look at this screen. Look at this screen, and there is a bar magnet. Notice one thing, there is no power supply at all. There is no power supply at all. Now, remember your question, huh? I'm moving the magnet now. Look at this, I'm moving the magnet. Can you see voltage and current there? in the bulb.
Yeah, sir.
Okay, now I hold the magnet. Okay, now I move the magnet. I move the coil. Can you see the current?
Yeah, sir.
So it means you can alter the magnet, you can alter the conductor. Now see the effect of increasing the number of turns. Do you think more current is produced?
Yeah, sir.
Now I am increasing more turns. Now look at this now. What happened?
Current increased.
Yes, a lot of new current has been produced. Look at the meter. 0 now when I stop. Now I'm pulling it out. Look the meter. Current is negative. Again, look at the meter. I stop the bar magnet. No EMF now. When I pull out the magnet, look, the current is negative. This is electromagnetic induction. A very comprehensive simulation. And I think I have shared with you one of it type. And it's a very nice, but it runs on PC, it runs on Windows, I mean laptop or PC, but not works properly on mobile phones because Java is there a bit, Java and Flash is there. Now, okay, now look at this screen. This is the bar magnet, huh? And I am moving the bar magnet towards the solenoid. Now, what is the observation? As you move, EMF is in, you leave it there. When you leave the bar magnet, no EMF is there. If you reverse your bar magnet, EMF also reverses. When you move the magnet forward, EMF increases in one side. Achha, if you move slowly, less EMF. If you move faster, the frequency is so high. So this is called Faraday law of electromagnetic induction. This is also a very nice animation if you see. This is a concept of iron core. There is an iron core inside the solenoid. And look, due to iron core, magnetic effect is stronger. There is an iron core which is enhancing the magnetic effect. So Faraday Faraday made some generalizations. Faraday now understood that you need motion, relative motion. You need motion, and without the motion, it won't work. And whatever you are doing, you need to provide some energy. If the bar magnet is not moving, EMF won't be produced. If the bar magnet is not moving, EMF won't be produced. Now look at this concept. When the bar magnet approaches the solenoid, flux linking the solenoid changes. Now, have we copied the diagram? This one, this one.
Yes, sir, I did.
Okay, good. So now you have to copy this screen.
Done, sir.
So you understand the main idea. The main idea is the change in flux linkage. Now you have to copy. You have to copy this screen. I'm just coming. I have to say Asar Namaz here. So please copy it. I'm just coming.
Okay, sir.
This was a formula in our AS physics. I is equal to NAVE. N is equal to number of free electrons per unit volume. And it is called number density. So greater the number of turns, greater the number of turns, greater is the amount of induced EMF. Greater the number of turns, greater is the amount of induced EMF. Now, these are numberless examples. This is another example. These are all past paper examples. You can look at this example. This magnet is spinning. It is spinning in front of the solenoid. So the flux cutting in the solenoid will change. But this time, the current is induced in a flickering way. Why it is flickering? Because the bar magnet is spinning, so it is getting closer to the solenoid and getting away from the solenoid. Secondly, north faces, then south faces, then north faces, then south faces. So the output is flickering, alternating EMF. This is a magnet, a spinning magnet. There is another famous example, example number 4. That is an electromagnet and a vibrating sheet of aluminum. You have to copy this screen. For the reference, you can put it example 3, because we have not copied example 3 here. So make it example 3.
Done, sir.
Now, the sheet is vibrating, and I switch on the electromagnet. When I switch on the electromagnet, magnetic field lines will begin to cut in the oscillating aluminum sheet. This will be a case of Faraday law. Field is cutting, field is changing. So according to Faraday law, EMF is induced according to Faraday law, and EMF is induced. Now, this is not a complete circuit. A circuit actually is having 2 wires, one neutral and one live wire, but this is only a sheet. A sheet is a short circuit, not a complete circuit. So when EMF is induced, it will spark. It will spark, and current will produce in small sparks, which are called eddy currents. Due to these eddy currents, the sheet will become overheated, energy will be lost, and oscillation stops. I repeat from the start. A difficult example. One of their favorite examples, it comes in this chapter and also in another chapter, which is called SHM, simple harmonic motion. Now, the sheet is vibrating in front of the electromagnet. We switch on the electromagnet. Now the sheet is cutting the field lines. Now the sheet is cutting the field line. It is just like you swap a card over a sensor machine like a credit card or debit card. It is scanned and the field lines is cut. Now the field lines is being cut, EMF is induced according to Faraday law. When EMF is induced, current try to produce, but the current cannot be a proper current because it's a short circuit. It's a sheet, not two wires. So current will break into sparks, which are called eddy currents. Now the sheet will be overheated. It will lose the energy of oscillation and stops. Now, after copying the diagram, you have to copy the concept map.
Done, sir.
Magnetic field linkage change induce EMF. Now, if the circuit is circuit is complete, full current is produced. If the circuit is not complete, it will be a spark. You have to copy this.
Done, sir.
This is flux, all the field lines. And look at this diagram. We have drawn it before also. What is flux linkage? The three lines which are going through the object is called flux linkage. For example, just imagine you are sitting in a room. The room is full of Wi-Fi signals. This is flux. Now, your mobile phone, from the total surface area of the mobile phone, now mobile phone is intercepting some lines. These lines are called flux linkage. See this example. Now it's a metal string, a metallic string, and a metallic string is vibrating. Metallic string is vibrating in a magnetic field. Look at the magnetic field crosses. As it is cutting the field lines, it will induce an EMF. and when it is cutting the field lines, it will induce an EMF. And once it induces an EMF, again, the circuit is not complete. It's a single wire. So as it is a single wire, it will induce sparks. Example 6, it's a metal disc, spinning disc. The disc is spinning in a magnetic field, and the disc is having some holes which are cutting the field lines. When the disc is moving like this, it is cutting the field lines. And when it is cutting the field lines, it will induce an EMF according to Faraday law. Now, see, give a heading, example. Numbering you can adjust because I'm not asking you to write all examples, not enough time. And obviously, this is a heavyweight chapter. So give the example, next example number, whatever is the next example number. And write that, consider a spinning disc. Consider a spinning disc in a magnetic field with holes in it, as it spins, magnetic field linking the disc changes. This induces an EMF. This induces an EMF according to Faraday law. You must have noticed that according to Faraday law is coming every time. CI says that when you want to justify, explain the induced EMF, you have two options. One option is the runaway option, that is refer to Faraday law and run away. Second, take the courage and give the whole theory regarding F is equal to QVB sine theta, electron shift. And this is a better approach, but definitely writing it needs more space. Faraday law is a shortcut. Faraday law is a shortcut. So we keep it up to here, and we will inshallah continue this in our next class. Allah Hafiz.
Thank you, sir. Allah Hafiz.